Okay, this is an example of a wheel rolling down an incline. You'll definitely find this useful for the rolling problem on the weekly assignment. So um, let's say we have, I'll do it this way. So let's say there's our incline, and let's say this angle is 30 degrees, and here's the wheel, okay? Um, and let's say that that wheel is a disc with a mass of 10 kilograms and a radius of zero point 0.2 meters. Um, and let's say we want to calculate the acceleration down the incline. All right, well, we're going to use the coordinate system that we use for um, rolling and sliding problems. That is the y-axis coming out and the x-axis parallel to the surface. So the y-axis always goes straight out of the surface. And we're just going to do this as a rigid body problem. We'll see that there's one constraint we have to do at the end. Okay, so to do a rigid body problem, first we have to think, is there a fixed point? In this case, there's not. Fixed, no. And so that means that, let's call this C, the center. The moment of inertia is about that point C, and it's equal to 1/2 mr squared, which is um, 0.2. Now that we have that, we can do the free body diagram. So there's a weight force down. This has a mass of 10, so this is 98.1. And there's a normal force. And there's one more thing going on that has to be going on for this to rotate. There has to be friction with the surface. If there's no friction, this will just slide down. So we won't get rolling without slipping. It'll just slip down like a block of ice. And so the friction force is opposite the direction of motion. It's perpendicular to the normal. And we don't have to use the coefficient of friction or anything. We can just treat this as some force F. That we'll be able to solve for that in our system. It's not something you want, that's very useful very often, but we will calculate it in our system. Okay, so that's everything. If you're pushing on this, then there'd be other forces or whatever, but this is all that's going on. Since we have a rotated coordinate system, this weight force isn't going to be just straight in the negative y direction. The angle for that is going to be 240 degrees. Or you can think of it as an x component of 98.1 negative sine of 30 and a y component of negative 98.1 times cosine of 30. All right, so let's go through the table. First, we have the weight. That's at the center of mass, so there's no row vector. The force vector is 98.1 times. So for the easiest way to do it numerically is 98.1 times cosine and sine of 240. For the weekly assignment, you'll want to, that gets a little messy. It works out a lot cleaner if you do it as 98.1 times negative sine of 30 and negative cosine of 30. You just have to think of the triangle and do the trigonometry. Okay, so the force vector there is negative 49.05, negative 84.96, no moment. And then the normal force, the row vector, well, you can see the line of action of that goes right through the center of mass, so that's also going to be 0. But if you, okay, but if you really did that row vector where that normal force is applied, this would be 0, negative r. The force vector is 0, and so you get no moment there. And then the last one is the friction force. That's also at the location 0, negative r. R is 0.2, so this is 0, negative 0.2. So is this one. The force vector, that's acting in the positive x direction. So that's FF0, and the cross product is positive 0.2 FF. There's no fixed point, so we do have to use Newton's second law for this. So we get negative 49.05, negative 84.96, plus 0n, plus FF0 is equal to, you can think of this as the mass times the acceleration of at point C. Okay, so there's two equations, and then the moment equation says 0.2 FF is equal to the mass moment of inertia times the angular acceleration. Okay, so how many variables do we have? We have 3 equations, and 1, 2, 3, 4, 5 variables. So that's not going to work yet. But anytime you have a rolling problem, you need to use the rolling without slipping equations. And the acceleration for rolling without slipping, the acceleration of the center of the object is equal to negative alpha r 0 if you're using this rotated coordinate system. And so that's negative 0.2 alpha 0. And now we can substitute that into Newton's second law. And we get the equations. I'm going to break it up into components. So negative 49.05 plus FF is equal to negative 0.2 alpha. And then the second equation says negative 84.96 plus n is equal to 0. And the third equation says 0.2 FF is equal to 0.2 alpha. And in this case, the arithmetic is easy, so I'm going to divide both sides by 0.2. Okay, so now what are we going to do? I probably should have substituted the other way just to save a step or whatever, but if I substitute alpha in for FF, okay, so I'm going to substitute this in. We get negative 49.05 plus alpha is equal to negative 0.2 alpha. And that says that 1.2 alpha is equal to 49.05. And so alpha is equal to 40.88. This is radians per second squared. So this is why I said this isn't the cleanest way to substitute, but this will work fine. What we know is that our acceleration is, our acceleration vector is only in the x direction, and it has a value of negative 0.2 times alpha. So the acceleration is only in the x direction, and it's equal to negative 0.2 times 40.88. And that is 9.76 negative meters per second squared. Let me just check that. Wow, I was way off. That is negative 8.176. Okay, so that's the approach for the kinetics of objects rolling down an incline. You also, I eliminated FF, but you could easily find the force of friction in there. And you're going to want to follow these steps to do the rolling problem in weekly assignment 2.